Okay. So you are, find your, okay. All right, so maybe you have one more talk related to CGI. Is this one? Is that the right?
No, like,
Oh, sorry. Great. By Alexis Lau on high order dithering, extending JWST small grid dithering strategies for Roman CGI.
Can everyone hear me? Okay, cool. So good morning, everyone. I'm Alexis Lau. I'm a postdoc at LAM, and today I would like to talk to you about how do we want to improve the post-processing detection limit by modifying the observing strategy with focus on Roman CGI. Yeah, so again, the really famous plot. The predicted performance of Roman, with the help of post-processing, we are hoping to reach maybe to the 10 to the minus 9 level after post-processing. And Roman also will be the first CGI, the telescope, will be equipped with deformable mirrors and enabling active wavefront sensing and control, which makes Roman an ideal platform to develop and mature techniques that requires deformable mirrors for future space observatory, for example, the HWO. However, for Roman, the baseline observing strategy is going to be RDI, and the post-processing detection limit is ultimately limited by how well the reference observations are going to be able to sample the residual speckle variations in the science images. So this limitation arises from the fact that we have a drift, because the speckles actually evolve in time. Meaning that when we are conducting the observations, there will be temporal reference drift, for example, induced by thermal deformations, like telescope mechanical movement, for example, the slew and the slow. And then these will induce what we call quasi-static speckle. And these speckles actually involve in a similar time scale as the observing time. So that means that the speckle realizations in the reference images might not be sample, might not sample what is going on in the science images. So for the James Webb Space Telescope, there is a technique called the small grid dithering that everyone has heard about, to partly mitigate the effect. So again, the idea of our strategy is basically based on the technique called small grid dithering. By applying, small grid dithering is a technique that actually apply a two-dimensional offset, controlled tip tilt, by moving the star behind the chronograph. By doing that, we would be able to actually sample different speckle realizations in the reference image library. And the reference image library would be able to have better variations of the speckle realizations and improve the overlapping with the science speckle subspace. So this technique has worked really well and has become a standard procedure of the JWST chronographic observations. So for JWST, it's limited to two-dimensional motions, but Roman, by contrast, we actually have deformable mirrors. So we will be able to extend the technique to even higher order mode beyond tip tilt. So here is showing the idea of how we're planning to extend, our group are planning to extend the idea of small grid dithering to even higher order mode by utilizing the deformable mirrors equipped on telescope like Roman. So by using the deformable mirrors, we are able to introduce controlled phase perturbations onto deformable mirrors. And these perturbations can be expressed in Cernicke, for example, model bases like Cernicke's. So the idea is that we will apply, similar to the small grid dithering strategy, we're going to apply these jitters during the reference acquisitions, leaving the science images untouched. So the idea is that if we have a richer PSA diversities in the reference library, we will have a richer model subspace when it comes to post-processing. So this work is being done within the landscape of ESCAPE. So yeah, this project is brought to you by ESCAPE. Not a sponsor segment, but I just would like to showcase our team, what we've been working on. Our goal is to develop modern post-processing technique tailored to active space telescope and enabling detections of cold giant exoplanets. And LOD Showcase, the PI. And Nicolas Goudot has been working on JWST data analysis, and Sophie Noé has been working on software developments within the Roman CPP context. Lisa Tinier, who's defending soon and also on the job market, she has been working on the simulations, focusing on the technique we call high-order dithering. And me, Alexis Lau, I'm working on the experimental validations based on the simulation results that Lisa achieved. So with that context, now I'm going to talk about how we verify the idea of high-order dithering. So to verify whether the idea of high-order dithering actually works or not, we combine the simulations and also experimental approach. So first of all, on simulations, Lisa has been working on end-to-end prototyping observing sequence. And then her work actually inform us a little bit more about, give us a more idea about how the achievable gain of high-order dithering evolves or depend on the injected aberrations, jitters, and also the drift regimes. And now we can see that in simulation it works. On the plot on the right-hand side actually showcased the representative study that she has done during her PhD. So it's time to actually test whether it actually works on the optical system. So to do that, we implemented the experimental sequence on a high-contrast imaging testbed called HiCAT. HiCAT is a system-level high-contrast imaging testbed operating at the 10 to the -8 level, similar to the Roman CGI context. So the idea is that bringing the experimental validations even closer to the Roman context. So next, I will go talk about how we mirror the experiments on HiCAT. So here is a nominal, what the cycle is going to look like. So after they dig the dark hole using the technique called the electric field conjugations, then the Roman coronagraphic instrument, we're going to start performing what we call the reference acquisitions. And then afterwards, it's going to move, the telescope is going to move to observe science target at a multiple row angle to enable angular differential imaging. So to simplify this setup, we are doing this. So since we actually cannot slew the testbed to a star, so we injected, we injected what we called a synthetic slew at 2 nanometer RMS with a linear combinations of modes from set 4 to set 29. And because starting from after the EFC, actually the loop is being left open. So the contrast level that we actually observed throughout our study is a lot higher than what we have, what is the nominal baseline of HiCAT. And we also let the natural drift accumulate throughout the observations. And this is going to be the baseline that we used to compare whether high-order dithering works or not. So now I'm going to show you how we actually implemented the technique. So you can see on the left and on the right, basically they are identical, except for the fact that we are applying jitter patterns during the reference acquisitions. So from here, it actually established the baseline of whatever performance that we are observing in terms of processed detection limit. We will have an idea of how well the high-order dithering actually are being able to sample the residual speckles within the science acquisitions. So the thing is, in theory, if we want to match the speckle subspace, we can inject as many jitters as possible, but in practice, it's not practical. So we have done a systematic study to down select the jitters, number of jitters and families. So in here, just showing is what kind of study we have done. This basically is the linear combinations of sonically pure modes, within the linear combinations, and also a mixture of the model contents. And we have explored different jitter amplitudes for the whole study, and we keep the identical setup for the observing sequence and the post-processing in our study. So here is the comprehensive study that we have done, and if you want to know more about the results that we have obtained on the on the testbed, please come talk to me, and hopefully we're going to have the paper being submitted soon. And for the rest of the talk, I'm going to talk about a best case scenario that we have observed throughout our study. So in here, what we can observe is we are able to. Okay, first of all, disclaimer. Because we are injecting slew and drift to mimic the observing conditions, our contrast baseline, as you can see in here, is actually higher than 10 to the -8. And as you can see in here, beyond 5 lambda over d, we can actually start to see gains when we applied high-order dithering in our reference acquisitions. And like we achieve up to 2.5 contrast gain, like between 7 to 8 lambda over D, within like a strategy called linear combinations, meaning that I have like single mode content within this radio group and also a mixture of the linear combinations within this radio group. Having established the fact that it's like, yeah, it works on the testbed, or in our particular case, I would like to show you how the strategy might be sensitive towards like the amplitudes of the dithers. So then this plot is showing, the dashed line showing is like the best performing cases for each method that I showed in the previous slide, like with the mixture of modes, pure modes, and also the single modes. And the shaded region in here is showing that like actually the gain that we can observe would be sensitive to the amplitude choice, meaning that having the right model content would bring us to the correct regime that would lead to contrast gain. But we are also sensitive to the amplitude, to the amplitude of the dithers, which is like kind of similar to what they have observed on JWST. For example, it's like small grid dithering technique actually would require like some tunings of like how far the steps needs to go in order to maximize the gain that you can achieve. So yeah, I don't have much time, so I'm gonna give you the key takeaway message and talk about what would be the implication on Roman. So high-order dithering as an extension or generalizations of small grid dithering actually enable us to capture, to better capture the spectral variations of the science observations, and it leads to the improved performance. And in the representative case that we have shown in here, it actually leads to like up to 2.5 post-processing gain, which is equivalent to Dmax equal to 1. And we also, oh, whoops, sorry. And we also find that the approach can remain operationally simple if the number of dithers is limited and making it compatible to Roman CGI. However, what we also know is that it's like the dithering amplitude and the model content identifications are required, like if we want to apply to Roman CGI, and then likely it will be informed by commissioning datas. So for like a future perspective to bring our high-order dithering technique even closer to the Roman context, to the Roman mission context, we would like to use like the OS11 data and like the Roman simulators to inform both the model contents and the dithering amplitude selections. Thank you.
We've got time for a few questions. All right.
Hiya.
Yeah.
Dimitri, go ahead.
Great talk. So yesterday we had a great talk from Marcus about how certain coronagraphs can be affected by, say, well, that's my theory anyway, low-order aberrations leaking in an undesired way through the coronagraph and affecting spectral statistics, which doesn't play well with post-processing methods. Here you're seeking an optimal set of aberrations to inject to improve post-processing, but I would be curious to see if your framework can also tell us which ones to avoid to degrade.
Yeah, I think it's like it's possible, but like as you said, it's like it will be depending on the coronagraph. So it's like I guess like we need to be done, like the study will need to be done based on different types of coronagraph, and I think it's like from the injections, and then when you actually look at the like the focal plane data, yeah, like you will have more information on like what modes to avoid and what modes to actually include into the sequence.
Any more questions? In the back.
Very nice talk and concept. Close to the star, one of the dominant terms in PSF variability for Roman, maybe HWO, were changes in jitter state and star size. Like right up against the inner working angle, you're always limited by jitter. Otherwise, you pick the wrong coronagraph to some extent. And the interesting planets are always right up against the inner working angle because the universe hates us. And interesting, I have a really terrible idea and a less terrible idea, but you could imagine wanting to probe different bits of jitter space. The really terrible idea would be to turn the reaction wheels up and down. The less terrible idea would be to deliberately detune the low-order control loop to sort of change the jitter from blah, 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 to blah, 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 to blah, 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 both on the science target and the reference target, sort of accept a degradation in performance in order to go through this really unknown space that you're going to hit as the spacecraft jitters around. So it could be interesting to, I don't know if that's something you've thought of, or it'd be an interesting side conversation to talk about.
Yeah, like we can talk about it later, yeah. But I haven't thought about that before, like I have to say.
All right, let's thank Alexis again.